Okay, in this video we will demonstrate at an overview level 4 example tutorials from the MBDyne website. Rigid body, rigid pendulum, chain, and then cantilever. So the model is in a file examples.blender, so we'll open that file and you'll see that we have 4 scenes. Rigid body, rigid pendulum, chain, and cantilever. We'll start with rigid body, and what we'll notice first is that we have a folder that I've created, which has, in this folder is the examples file which we just opened. And if we go into the folder under it, which is of the same name, examples, we'll begin to see this populated with the input files for the various models. So for instance, if we go to this rigid body and we click on this, we now could run the simulation. But before we run it, if we go to the folder, we see that this rigid body file has opened. If we look at that, this was just generated by that click, and we see here the specification, and this very closely matches the specification from the website for all 4 of the models. So if we go here, for instance, to the website for Blender and we click on rigid body, you'll see the same kind of input specification for this model. So what I'll do very briefly in this video is just go through each of the 4, and there'll be subsequent videos that shows the step-by-step build-up of these models. But so we created the input. If we run the simulation here and then animate the objects, the same, animate just say one every 100 objects or so, then what we'll see when we click go is we have, if I go and walk through this, we have a body, which is this here. I'll change the change it. So we have this body, we have a rigid offset, which is pointing in the Z direction, and we have a structural force, which is also pointing in the Z direction. That's the force which simulates gravity in this model. And then we also have a frame. If we click on the reference frame, you'll see that the brighter of the two, that's the frame, and it's pointed in this direction. And then the body here is in that frame. And if we look at what the frame specifically is, we'll see that it has a linear velocity vector and an angular. And the linear has a unit in its own z, which is in the direction of that little arrowhead or pyramid. So if we click on this, for instance, we'll see that unit vector is 0, 0, 1, right, in the z direction. So it behaves as you would expect, which is as we animate, initially the only velocity is from the reference frame, where it's moving at 1 meter per second in the y direction, and then with the acceleration of gravity, which is simulated by a force in the an absolute force in the z direction, it just goes like this. And by the way, that absolute force in the z direction, we can look at that here. The structural force, again, if we click on that structural force, it's from that rigid offset, which is pointed in the vertical positive z direction. And if we look at that force, we edit it, we'll see that it's using this constant minus 9.8, which that's just the name of the drive. If we look at the drive, and it's an absolute force, if we look at the drives, we'll see we specify that to be minus 9.8. So okay, so that's the first, and we'll come back to that in another video. Next, we'll look at the rigid pendulum. The rigid pendulum is interesting with having a reference frame which starts this in motion. Let's begin really by just looking at the various elements. We have a clamp, which is here at the origin, 0, 0, 0. And then you'll see later why we've rotated it so it points in the what does it point? It points in the minus y direction. But so we have this clamp, and then we have a revolute hinge, which is at the same location as the as this. And by the way, the revolute hinge is connected to the clamp. So we have a clamp and then a revolute hinge connected to that clamp. And then we have another revolute hinge, which is where the mass will be. And that revolute hinge is here, and that's connected to the revolute hinge above. We have gravity, which of course has no vector at all. Unlike the other model, this one is truly a gravity element. It's not an absolute force. And then we have this body, and the body is at the same node as that, or at the same location as that second revolute hinge. And then the other part to look at here is the reference frame, and you'll begin to see here now why we had the clamp, right? So we have this clamp which is pointing that direction. That's also the reference frame, and that reference frame is causing this. It only has one element in the frame, which is this upper revolute hinge, and that upper revolute hinge reference frame in the linear velocity is 0, and the angular velocity is 0.2 in the z direction, and that's because well, it's in the z direction of our reference frame, and our reference frame is pointing that way. So if we go and look at our reference frame, that's just the name of that vector. If we edit the vector, we'll see that indeed the vector is 0, 0, 0.2. Okay. So now if we if we go and click initial value, that'll produce the input, and we can go again now to our examples folder, and we'll see rigid pendulum. We have the input file. If we edit this and we look through it, it looks very similar to the one on the website for, let's see here, get there, yep. So it looks very similar to the website demonstration for rigid pendulum, right? And again, in a future video, we can go through this in a little more detail. So if we go back and animate this, or first run the simulation, and then animate it, this should look familiar to those who have performed the original example. So here we go, we'll animate it, and there we go. So we've got the body, and see the body has no rotational motion. It's just moving back and forth with the pendulum, and the pendulum is moving because of the reference frame. Okay, so next we'll go to the chain. The chain is made up of quite a number of elements. So again, we'll start with this clamp, and the clamp is at the origin, and then we added a first body, which, as you'll notice, the shape of the body is represents the inertial matrix of that body. So if we look at the body itself and see there's its location, and we properly specified its location. Again, later we can show how to build that up. And then the matrix itself, if we look at that, you'll see it's a matrix of 1, and then 0.1, and then 0.01. And the way this tool works, it kind of morphs the shape of the body to represent the matrix. So you'll see kind of a 2 orders of magnitude depending on which direction you're looking at there. So okay, so that's the first body. We can look, there's the second body, third body, fourth body. All right. Now, after we did the bodies, and we have a rigid offset from these bodies. So the first rigid offset is, well, this is a rigid offset from the clamp, which is at the origin. And that's where our first revolute hinge will be. Or actually, I think it'll be a spherical hinge, yeah. So then our next one, which is connected to this chain link, and then our next one, a next one, a next one. So those are all rigid offsets. This one here is in a different orientation, you'll see, because we use that to initialize the simulation. Next we have, if we go up here, we have the spherical hinge, and that spherical hinge is at the it's at that rigid offset. So as far as the modeling is concerned, it's really not the rigid offset. It's attached to that first body. So we do the next spherical hinge, the next one, the next one. So we now have all of our spherical hinges. Next we have our deformable hinges, and these are kind of deformable revolute hinges, if you will. So and this will provide some damping, right? And if we want to look at what the damping coefficient is, we can go in and edit this. We see that this is the linear elastic constitutive. If we look at the linear elastic constitutive, it will see that's a 6-dimensional constitutive with a stiffness of 0.1. Again, that comes from the example at the website. So if we go through each of these, we'll see that's our first deformable hinge. Next, next, next. Okay, so now we have the damping, and next we have gravity. And I think the last piece here, yes, is how we set this up. So we have an inline joint, and what it does is again, remember this is offset from this link. It's a rigid offset from that link, and inline keeps that inline in relative to the to this clamp. And if we look at that, I don't know if there's anything to see here. There's really nothing to see. The next thing, though, to see is that we've made this driven, and you know, the simulation has it set up without any motion for the first second, and that's done, of course, with a drive, a string drive. We edit, we'll look at it. This is time less than 1. So what we've done here is we have this driven element, which really is this string drive, which drives the inline element, and so that holds it in place for 1 second. So with all that, we don't have any frames. We can see here there's no frames, reference frames, so everything is in the global frame. And if we click initial value, again, just for the completeness, I'll go back here and look at the folder, and in the folder you'll see that we should have, yep, there's the chain file. And if we edit it, you'll see first we have a description of all the pieces. Again, a future video we can go into this in detail. We have all the nodes, we have all the elements, and there you go. So again, if you run the simulation, you should see the exact same results that I'm seeing here. And then we'll animate the object every 100 steps. And I'm just going to step through it pretty slowly. So you can see, there goes the chain, right? So the one thing we don't have on this compared to the example on the website is we don't have an extra mass on the end. But other than that, it's basically the same. And this kind of behaves as you would kind of expect. I'd kind of like to see a little more damping in it because I think it's a little too active. But and it doesn't have any air properties, so there's no aerodynamic damping either. So it's just kind of really moving. Okay, so next and last is the cantilever. So with cantilever, there's not a lot of motion here, and that's just the way the example was created. But again, we can just walk through this and see that we have a clamp, which is at the origin, and then we have a first body, which is here at. If we really wanted to see what the location is, we can just hit the N button, and then we can see the transform, and we see that. Well, I can't see it too well because of this, but well, hold on, let's get this. I want to be able to show you that it's a half unit away, right? So it's x direction 0.5. So that's a way to be able to see what the precise location is of any body. So anyway, so that's the body, and if we wanted to look at its properties, we could edit it. We see that its mass is 0.25, and then if we wanted to look at the matrix, we could look at the matrix too, but we won't do that for right now. Then the next body is here, and it has its own properties. Again, that comes from the example. So those are the only 2 bodies. And then we have this first beam segment, And you'll see that we have represented this so that they look like these bricks in the form that you would expect of an I-beam. So X is in the proper direction, Y and Z. And then we have another beam segment, and then what we've done is we've joined them into a 3-node beam, and the constitutives are, again, according to the example file. Then we have this rigid offset. This is 1/8 of a unit inward from this last beam element. And then we have a structural force, which is at x equal 1. And we actually have 3 structural forces, and this is interesting how the model was set up. One, we have an absolute, and this is at 100 units, constant. In fact, we can look at that. See, it's 100. We have another structural force. This one is a follower at the same 100, constant. And then we have a third structural force, which is a absolute orientation, and it's using an array drive. And if we click here, we'll see that the array drive is made up of a sine drive and a cosine drive. So if we actually go down to our drives, we look at our sine drive, we'll see it here. All right, so here's our initial time, the omega, the amplitude. This is an infinite cycle, and then we have our cosine drive, which is this just goes for a half cycle, and then our array drive is just made up of those 2 drives. So the meter drive, by the way, here, this is just for running the simulation. So let's run the simulation, and that'll be the last activity for this video. So we'll run it, and then we'll animate it. It's every 100. Okay, and then if we just play the animation, we see the beam. Kind of, you can see it there. It's moving a bit as you would expect. Okay, so that's all for now. We'll get back to you in the next video.